Hello and welcome to the third keynote lecture on this conference. The keynote speaker will be Professor Silvia Ghilezan. She is a professor of mathematics at the University of Novi Sad and Mathematical Institute of Serbian Academy of Science and Arts. She also held visiting positions at several universities such as University of Oregon, École Normale Supérieure de Lyon, Université Paris Diderot, University of Turin, Radboud University, and McGill University. The major lines of her research are in mathematical logic and application of programming languages, concurrency, and mathematical linguistics. Her current research interest includes formal methods for new challenges in privacy protection and artificial intelligence. She has initiated, assembled consortia, and project managed several successfully completed projects under national and international programs. She collaborated with over 70 co-authors on publications in leading magazines, books, and editorials. She acts as a steering committee member of FSCD conference, an advisor for industry, a popularizer of science, and a promoter of gender balance in science. She supervised and influenced a good number of students and researchers, of which I am one, I'm happy to say. She was awarded the distinctions Chevalier and Officier de Ordre de Palme Académiques of French Republic. Today, Professor Ghilezan will give us a very interesting lecture entitled Type Systems for Trustworthiness for Mathematics, from Mathematics to Large-Scale Systems. I'm eager to hear the lecture, as I believe are others as well. So, Professor Ghilezan, please take the floor, or should I say camera, back to studio. Thank you.
Thank you very much, Professor Đukić, for this kind introduction. I'm really honored to be invited to give a talk at ECBS. First of all, I would like to thank Professor Popović for bringing this conference to Novi Sad. It is very important for the community, for boosting the community in Novi Sad and in the region, and also to even more establish Novi Sad on the map of the ECBS community. Also, my thanks goes to the organizers. The organizing team led by Professor Bjelica has done a good job so far, a great job actually, since it's not easy to make this large-scale system work and be reliable as it is. So I wish you to continue and to close the conference in this way. When I was invited to give this talk, so first of all, I was thinking, I am a mathematician. Usually our talks are packed with formula and packed with proofs. But nowadays there is a lot of exciting talks around the space, the digital space. So then it's really difficult to give a talk with a blackboard and the chalk that we still do with our students, even online. So I decided to go to a high-level talk and to talk something about formal methods and how theory can maybe tackle some problems, maybe can add something to the solution, and but at least it can consider all the problems, most of the problems that that we face nowadays in everyday life. What I will speak mainly about type systems. That was my major subject of research when I started a long time ago, and type systems have evolved during this period very much, and it is very interesting to evidence how research and how science develops, and actually how application then goes. So we go hand in hand with application, of course, much slower than the applicational side. So what is basically a type system? Type systems have gained an important role in the analysis of formal systems. And what is the type? What does the type system do? So the type system takes the language of this formal system, the language which consists of terms, and then splits it into sets. And these sets are actually meant to prove absence of certain undesired behavior in the language. So as you may see, this is a very general notion, and it can be applied really in very, very different contexts, which I will try at least to give you an insight. I will start from mathematics because type systems started in mathematics a century ago. So now it's really a century the type systems are developed in mathematics in order to prevent some paradoxes that occurred in the foundation of mathematics. Then I will give some idea how types entered computation, and especially in Lambda calculus, and how different types such as functional, polymorphic, higher order dependent types evolved and now became really very important in proof assistance in automatic reasoning. Also, I will tackle the application of types in programming languages. Of course, I will not go into the mainstream application of types, since I'm much less knowledgeable than the audience is, but I will point out some specific roles of logic in programming languages, especially in the control of duality of computation, such as call by value and call by name. Then moving forward, how time moves forward, we come to concurrency and to distributed systems, where our research and what we have done actually is in the domain of control of communication, of process calculi, underlying process calculi, with so-called session types and behavior types. And finally, we will get to the large-scale systems where types can be a good mechanism to control access and to control privacy and to control privacy issues in environments such as linked data, digital contact tracing, and currently in blockchain. So this is the outline of the talk. The previous slide is outline of the talk. I will consider types in all these five paradigms, 5 different environments, and also share some of our results that we have managed to obtain in some of these domains. Of course, we don't have any results in the beginning in the types in mathematics, because this area started 100 years ago. It is still very active, but it is a new kind of research now going on. So it started when George Cantor announced his naive set theory, meant to be the foundations, rigorous foundations of mathematics at the end of 1890s. It was not an axiomatic systems, but it was something towards the our axiomatic systems. Nowadays, it's called naive, since it's not fully axiomatized. Very soon after this this theory was presented, Bertrand Russell, a famous British polymath, gave beginning of the century, came out with an example, with a question actually. So let us consider this expression: S does not contain itself. And construct a set R, according to Russell, which contains this object that don't contain themselves. So then the question is, does R contain itself? If it contains itself, if it's an element of itself, then by this property, it is not contained itself. On the other hand, if it is not contained, if it does not belong to itself, then it belongs to itself. So this is something that is nowadays very well known as the Russell paradox. And this proved actually the inconsistency of Naive's set theory. And then things really had to be repaired from scratch because this didn't work. A way out from this paradox is something that Russell proposed. That was something that at that time it was called a hierarchy, a stratification, a hierarchy, a stratification. So dividing the language into some smaller sets. And this is something that is nowadays called type theory. So in this hierarchy, in this stratified hierarchy, this kind of predicates are not possible. So you cannot consider this relation that an object contains itself. It can be an element of an object from a different type, from a different class, stratified class. And this is the basis of type theory in mathematics. It helped a lot. So this was the way out. And this is how types became a way to control such kind of undesired behavior. Okay, so let's move in the second paradigm. Let's move to computation. Again, some history, because history is something that we have to learn and we have to digest and then to apply it for nowadays problems. This is how things work. Again, at the beginning, at the turn of the century, there was a very famous congress, mathematical congress in Paris in 1900, where David Hilbert, at that time, the mathematician of the world, so he was really the most prominent mathematician at that time, he came out with his program. How will mathematics develop in the next century? He proposed something like 23 problems, and it was really how mathematics developed in the 20th century. Some of these problems opened new areas in mathematics. Some of them were solved. Some of them are not yet solved. So there is a chance. What was Hilbert's program? Hilbert's idea was to provide a secure foundations of mathematics. This was very important for him, and not only for him, it was important actually for humankind, for all of us. So he raised some questions like consistency, completeness, and we will tackle nowadays, today, the decidability problem. Of course, it was this German word, which I never pronounced well, so I will leave to German-speaking public. Mathematicians started working on these problems. So all these nowadays very famous mathematicians like Gödel, like Turing, Church, they started to work when they, when they came to the age that they can contribute to these ideas. So Alonzo Church worked on the foundation. He wanted to formalize mathematics based on the notion of function. So not on the notion of sets like Cantor did, but on the notion of function, especially because decidability. Okay, so finding a procedure which will be infinitely many steps, give the answer whether something is invalid in a system or not. he approached via the notion of functions. So he defined everything in terms of functions, and of course it turned out to be an inconsistent theory. But the the part that was meant to formalize computable functions is nowadays called Lambda calculus, and it was a very successful model. He managed to give a negative answer to this Hilbert question. So he gave a negative answer to the decision problem, proving that there is no function which can compute whether two functions are equal or not. To most of you, this reminds you on the halting problem by Turing, and actually it is the halting problem of Turing. However, it was proved before Turing has developed his ideas. So in the mid-30s, yes, and Turing was a student of Church. So at that time, they were somehow interacting, and they had exchanging ideas. So as I said, many people worked, many mathematicians on these problems, and the ideas were floating around. In the 30s, this was, there were several other proposals for computable functions, such as recursive functions, combinatory logic, Turing machines, just to mention a few, and they were proven to be of equivalent power. So everything that is definable by recursive functions, it's definable by Lambda calculus, it is definable by Turing machines. And this is actually somehow the limit of computation, and it is nowadays called Church-Turing thesis. So what is Lambda calculus? Lambda calculus is nowadays very well known, although I dare say our students really, even nowadays, undergrad students, but back maybe 15 years ago, Lambda calculus was not that popular because functional programming was not that popular. So it was really maybe on the level of PhD studies, students got in contact with Lambda calculus. Nowadays, I dare say that even second years undergrads have some ideas about this. So the language is very simple. The languages of functions. So what do we have in a language in a function? A function is applied to a function. This is what we do. A function is applied to an argument. And there is another operation that makes a function out of some term. So this lambda xm, it means that we had the term m, and now it became the function of the variable x. So how do we compute? What is the reduction rules? What is the operational semantics of lambda calculus? We apply the function to its argument, let's say x, and then we compute this expression. If we apply the function to the argument 5, then in this expression, we substitute all occurrences of x by the number 5. And this is how the reduction goes. This is our intuition, but this is also a formal definition in lambda calculus. So this would be a formal definition of substitution. If we apply a function to an argument, a function m to an argument n, then we reduce it to an expression where in m all occurrences of the variable x is replaced, or the occurrences are replaced by the argument n. So in this very, very simple setting, Church managed to define everything needed for a computable function. So he defined natural numbers. He defined all the operations such as addition, multiplication, etc., recursive functions, etc., etc. Among these lambda terms that are very important is the so-called fixed point operator. It's denoted by Y. So it is an operator that makes fixed points of a function. It generates all the fixed points of one function because it reduces in this way. So it reduces in the way that it takes out in the head position the function f. In this way, it generates all the functions from the least generates all the fixed points from the least fixed point, which is related to the induction principle, to the greatest fixed point, which is related to the co-induction principle. However, you can see the computation is infinite. There is another important lambda term named omega, which has even worse computation, so it always reduces to itself. So this is an infinite loop of computations. This is something that might be not the desired property, what we want from a computation. We would like to have the result of the computation. So we would like the computation to stop. So let's stop it. Who will stop? Types will stop, of course. Types will control computation. So types are syntactical objects that are assigned to terms. There are two, and the aim was to stop the computation, so not to have any more infinite computations. Nowadays, it is very well known that there are two typing paradigms. There is a typing paradigm a la Curry, which is called implicit typing. So the types are assigned to the terms. The other paradigm is a la Church, and this is called explicit typing, where types are built in the term. This is interesting to evidence such kind of developments. For instance, when I was a student, this distinction between different typings was not yet singled out. So the first books on lambda calculus that I read, it was a kind of mixture of implicit and explicit typings. But nowadays, this distinction is very clear. So let us just see maybe the simplest types. The simplest types in lambda calculus are the functional types, but nobody calls them anymore functional types. They come from the notion of function, but nowadays they are called simple types. So they represent something like functions, where sigma arrow sigma represent a function from sigma to any other types, so sigma tau or whatever. It is meant to represent the function, but as we will see shortly, it is actually the implication in logic. So this is a logical connective of implication. And how does type assignment work? So we take a term from a language of the lambda calculus, we take a type and we assign sigma to this term m. So m is of type sigma. What are the benefits of this typing? First of all, there is this property called subject reduction, or it is called sometimes type preservation under reduction, which says if we have a m of type sigma, and if we reduce m, does not matter in which way we reduce, we just reduce in several ways, then this contractum, this p, which is called contractum after reduction, the term after reduction is of the same type sigma. So as you may see, if we consider types as sets of terms, so reduction is not taking out the terms from one class, from one type. This is actually the idea of Russell, but it is now in computation. So, as it is said, evaluation of terms does not cause the change of type. And this is also referred to as type soundness. So types are sound with respect to computation. This is something that gives trustworthiness to computation. There are more properties. So something else that is also very important is the property of safety in computation, which is preservation, the previous property, and also progress. What is progress? You, of course, know that better than that I as a mathematician, but progress from the theoretical point is something that ensures that things are developing and that we will end the computation somewhere calculating the value. So why do we do the whole computation? We compute in order to calculate the value. So progress is ensuring us that we will certainly get to this value. No matter what is the value, that we can define values in different ways, but we will we will get to our target. So these are something like properties that makes computation trustworthy. These properties are in this framework, the properties of trustworthiness. There is one more very good thing about these simple types is that they really do what they were meant for. They control the computation and do not allow infinite computation. So if a term is typable, then it is strongly normalizing. This is this expression used here. It means that every computation terminates. So there is no infinite computations anymore. This is a very important property, and it is. It has been, there are different ways to prove these properties, and these methods like reducibility, arithmetical methods, they are now standalone methods that stemmed from this very property. And again, what's going on? Who is controlling all this? This is all thanks to types due to types. So, the system of simple types is one down here in this spot, lambda arrow. This is the simple type, and there is a variety of different type systems that are systematized in the so-called lambda cube or Barendrecht's cube. So this is a system of 8 different type systems that are now put into this framework, and they really are extensions of each other as it is in this cube. This cube is this is also something that didn't exist 30 years ago. And I was somehow witnessing the development of the cube since I was the PhD student of Henk Barendrecht. So I was at that time when this cube got its form and how they were discussing how. So these systems were out there, but they were not systematized in this way. This is also a very important thing in research and in science, to put things together in a nice, elegant way and to make easier to comprehend. So these are all different type systems. I will say something more about them, but let's just point out their main property, and their main property is strong normalization. meaning that if a term is typable in any of these 8 systems, then M is strongly normalizing. So all its reductions are finite. There are many more type systems around, but they are not in this cube. There are systems like intersection types, recursive types, and so on. I will just mention this this reference book, Lambda Calculus with Types by Barendrecht, Dekkers, and Statman. I had a small, humble contribution in this book. Actually, the contribution was based on this 2000 paper about lambda terms cut elimination in different environments. Okay, so let's see the connection with between computation and logic. Computational interpretation of logic, which is nowadays called Curry-Howard correspondence, since it appeared first in the ideas of Haskell-Curry in the 50s, but it was published first by Howard. He gave several talks on these topics in the 60s and published in the 80s. So you see how it was just maybe 50 years ago. Some ideas were developing for 30 years before they were published. This is the connection with what is the logic of simply typed lambda calculus. So this was the question: what is the logic? And the logic of simply typed lambda calculus is intuitionistic logic. What is the connection? So we have this M is of type sigma. So a term is of types of sigma if and only if this sigma is a theorem of intuitionistic logic. So this connection is called formula as types. So formula in logic are types in lambda calculus. Then proofs in logics are terms in lambda calculus. So this term M encodes the proof of this theorem, which is actually the most important thing in constructive logic and constructive mathematics. The proofs have to be constructed, and this term is the construct of the proof. And nowadays it's called proofs and programs. And just to mention and point out, this is not classical logic, this is intuitionistic logic. So the most famous theorems from classical logic are not valid here in this framework. So for instance, law of excluded middle, contraposition, Peirce law, etc. are not valid in this position. But we will come back to classical logic a bit later. And now something about the logic of the cube. So these 8 systems, they all have corresponding logics. So this corner lambda arrow is the intuitionistic logic, and all its extensions are different extensions are logic of this computation. So we have these computational models of this logic. The left plane is a propositional part. So first order, intuitionistic logic is extended to higher order logic. So this is second order logic and higher order logics. And the right plane is the predicate part, and these are dependent types. As we saw, all these systems have the property of strong normalization, which is also very good is applicable in logic. There are these types called intersection types. I was doing some research, actually, my thesis was from the intersection types. An interesting question and still open question is, what is the logic of intersection types? It is not yet very well known. There are several approaches to this problem. But what is the interesting thing of intersection types? They completely characterize the strong normalization. So for all systems, we have this implication. If something is typable, then it is strongly normalizing. On the other hand, the equivalence holds for intersection types. So they type all strongly normalizing terms. This is really a very outstanding property of intersection types. So let us see how this cube corresponds to programming languages. These are functional programming languages mainly. So the left plane, it inhabits Haskell and Clean. The right plane, on the programming language side, it's Coq and Agda. Coq is actually the system of the most powerful system here, P, Lambda, P, Omega. So part of the system is actually, this is where Coq lives. Intersection types, there is a programming language called Foresight, which is based on intersection types. And what we do currently is probabilistic reasoning in type theory, so invoking probability to reason about type theory. This is now ongoing work. I will not go here into the details about the publication. What you may see, they span from 96 to 2000 to nowadays. I wanted just maybe to point out that in this area of research, I really collaborated with a variety of people. First of all, very distinguished people such as Barendrecht and researchers, and Mariangela Dezzani, who was the inventor of intersection types, but also I worked with very young people, with students, starting with Viktor Kunčak, Silvia Likavec, and then Jelena Ivetic, and nowadays, today, Simona Kašterović is the student. Of course, Nenad Savić was also a student, and also to mention Jose Espirito Santo. So I think that it is really that was very interesting work with this colleague from Portugal that we collaborated. Let's move further. Let's move to the types in programming languages. Here, what I will mention is the role of classical logic. We have seen that classical logic has no meaning in computation of lambda calculus, of the lambda cube, and of these programming languages that I mentioned. So for a long time, there was even a statement from distinguished researchers that classical logic has no computational meaning. But then it started in the 90s with the seminal paper of Griffin in the 1990, who gave the formulist types notion of control. Very soon, Michel Parigot presented the algorithmic interpretation of classical logic. It was leaked to 1992 in Montreal. I remember his talk on these topics, which was really a huge novelty. And this was in the natural deduction framework of logic. And in 2000, Curien and Arbelin came with the symmetric lambda calculus, which completely embodies the duality of computation in a sequence-style logic. These three modes of giving logic are the modes that are nowadays recognized how a logical system can be given: axiomatic, natural deduction, or sequence. So here, what happens? Peirce law, which was not inhabited, and it was out of lambda calculus and computation. Peirce law is the type of the call with the current continuation operator in the programming language scheme. So scheme is a language that is based on classical logic, and later on there were also other control operators are typable by classical tautologies. It's not only Peirce law, then the law of excluded middle and other theorems that are not intuitionistic, but they are very important role in control operators. So what happens here in this duality of computation? So the full system of interpretation of classical logic is non-confluent due to a critical pair. This is usually not good. I mean, if it's not confluent, then if you start the computation in one way, you can end up in one value, and if you go in another direction, in another value. So this is not, but this is not surprising, since classical logic in its full power has this a property that is called that cut elimination is not confluent. So these two properties, non-confluence in computation and in logic, embody each other. But there are two confluent subsystems, and it was shown one corresponds to call by value and the other corresponds to call by name. So both of these are strongly normalizing, and this is proved by CPS translations into simply typed lambda calculus, which is also now a very well adopted method on its own. And the characterization of strong normalization is also done by intersection types. So once again, types are the one who control duality. There is still ongoing work in this domain with some group from the US and from France. We still do some research in this direction. Here, what I wanted to point out, so this is a collaboration with colleagues from the US and France. And we had, this was the first result in 2004 and 2005 to completely characterize strong normalization in this dual calculus. Later on, these methods have been developed by other researchers, and it really became an area of research which is active nowadays still. Also, I wanted to point out our POPL paper, and this is the approach to call by name delimited continuations. So this was the first attempt to consider a delimited continuation in call by name setting. Up to then, it was only in call by value. And then we move to the fourth paradigm, to concurrency. What happens in concurrency? The Curry-Howard correspondence is extended. So on the left-hand side, we can see the Curry-Howard correspondence between lambda calculus and logic. So we have computation, but now in concurrency, we have communication. So it's not only computation that we care of, in concurrency, we care of communication. So computation was deterministic, communication is non-deterministic. Computation was based on terms, communication is based on processes. In computation, we have sequential composition. In communication, it is concurrent. The reductions were about computational behavior. Here, the reductions are the interactional behavior. So the interaction between processes by exchanging information and data. Lambda calculus was the base somehow of computation. In communication, we have different formal systems that are very, there is a plethora of different formal systems for concurrency. Here, I will just point out PyCalculus because we were mainly working in PyCalculus and in type systems in PyCalculus. So the Curry-Howard paradigm extends. So in this framework, the Curry-Howard paradigm is extended by the paradigms of proofs as processes. So everything stays as it was, but it is now extended since the formal systems developed. So what ensures, so here we will not speak anymore about trustworthy computation, but what is worrying here, what is worrying us is communication. So we want to make sure that our communication in these new systems in concurrency is trustworthy. There are several actually, there are very many type systems proposed for this purpose. Here is just a short list I was working on. These are behavior types for communication center systems. They ensure that the type system obeys the prescribed security policies, like access control, secure information flow. So this is what behavior types are meant for. In this way, so this is the property, the trustworthy properties that they ensure. Session types, on the other hand, allow interaction to be structured into basic units that are called sessions. And then multi-party session types are in the extension of session types. So they allow synchronous and asynchronous interaction between multiple participants. Today they are used for smart contracts, and that's probably one of the main applications of multi-party session types. What are the properties that we want to ensure with the type systems? What are the trustworthy properties that we wait for the system to prove, to ensure us that it will happen? Here, there are properties, the properties that we care in this context are the properties of safety and liveness. I will mention just two of them. So again, everything is based on subject reduction. So the type system is sound with respect to the reduction rules, meaning that if a process is typed, if it is well typed, then the reduction of the system will not change the type. Safety in this abstract way is actually the safety that is in computation as well. So it consists of preservation and progress, which here in concurrency, we say, well, nothing bad can happen during the communication if the term is typable in some of these mentioned type systems. But there is another thing that is very important in communication, and that is liveness. Liveness is ensures us that something good eventually happens, in the sense that if a process is typed, then all bad things that could happen are going to be avoided in some way. So all messages will be delivered. So in this typed process, all messages, there will now be an orphan message. There will now be deadlock. There will now be arity mismatch or race competition or these undesired behaviors. However, liveness is very difficult to achieve in these complex systems, but types are here to control this communication, and they will enable things to happen. This is the line of research that started in Novi Sad in 2005. So since 2005, we had a very, very lively interaction with researchers in this domain. We participated in several EU projects and have very interesting result and collaboration from this project. Again, so I would like to point the newest research in this is POPL 2021, January this year, and here we spoke about this very, very important property, liveness in this very involved setting of multi-party session types for the asynchronous calculus. We have managed to obtain, to use some kind of subtyping, subroutines in order to achieve liveness in this very involved setting. This work was, when we published the work, we found the notes back. So this work was done over 7 years. Of course, not all the time, but we started 7 years ago thinking and approaching the problem, and finally we got to the solution. Well, in these settings and somehow connected to the keynote of Professor Kostas Bush and the work of Professor Popovic, I want to mention this collaboration between these two groups of researchers, theoretical and the group from the computer science, the department on trustworthy transactional memory. What we have done is to formally verify, so to ensure trustworthiness of Python's software transactional memories developed by Professor Popovic. The first approach was using timed automata and corresponding tool UPAL. This result was presented at the ECBS 2017 and then further developed. And the second approach was to formally verify Python software transactional memory by a semantical push-pull model. This semantical push-pull model is really a very nicely developed theoretical piece of work, which was very well suited, and we managed to prove to formally verify developed transactional memories. And it's also my pleasure to say that this first result was firstly presented at the ECBS 2019 and further developed with Professor Popovic and his collaborators. And finally, coming to the end and to the larger setting, the large scale systems, and to the current research. So what is trustworthy worthiness here? It is of course computation and communication, but much more. So here we have a quest for safety, but also for security and privacy. And type systems again have a tiny role in all this, and they also can do something and can offer some solutions that can be may be useful in real life and in practice. Again, the type theoretic thing is subject reduction. So if we do a typing system for these huge environments, for these large scale systems, the thing that we have first to prove and that we first prove is subject reduction. So nothing will go wrong if we type. And then we can prove some several security and also privacy properties, not only some privacy, but the basic privacy properties that are given by the now well-known taxonomy of privacy, which is data collection, data processing, access to data, and data communication. The four taxonomy of privacy. Again, the types can control access. So they can control access to data, and that is what we have developed in our approaches. What are the systems that we typed, that we developed type systems? First, it was linked data. So this was some results from 2015. We started extending type systems of concurrency in order to obtain a type system for linked data, and we proved the privacy properties of this that are obeyed in this setting. And then we further developed these results to caller ID application. And recently we are working on privacy problems and overlay systems for digital contact tracing applications, which are used nowadays all over the world in this COVID pandemics. So these are all different things that have been done, ensuring trustworthiness of parts of these large-scale systems. The ongoing work is in blockchain technology. And what I wanted here to mention, I was attending yesterday a panel on digitizing consumers with the question, can we go back? And I think that my talk is somehow addressing this question, can we go back? There is no need to go back. We have just to go forward and to use everything that we have back. So this would conclude my talk. So instead of conclusion, I will quote again Lord Bertrand Russell from the beginning. So there are several interviews on YouTube. I like to listen to his interviews. It's a very historic and a very fantastic evidence of a huge intellectual. So he was asked, what do we have to learn? And he said that one of the most important things is to learn how to change beliefs and not to change hopes. So what we are doing in research is actually implementing this idea of Russell. We are changing paradigms. The paradigms are changing over time. So it was mathematics, and it was computation, logic, communication, large-scale systems, and new technology will bring new challenges, new paradigms. And what we have always to hope is to ensure trustworthiness in all these paradigms. And of course, I would propose to use types, and types can give at least a tiny answer and a tiny contribution to our quest for trustworthiness in different frameworks. So thank you for your attention. That was my talk. maybe a bit longer, and I hope that you will have a good lunch.
Thank you, Professor Ghilezan. Since we have a lunch break, so we do have enough time for as many questions as needed. And I will probably start with very simple question. It's regarding something that's clearly not the main topic of this talk, but kind of caught my attention, and maybe it would be interesting to some other listeners too. When you were mentioning the implicit and explicit typing a la Curry and a la Church, and from some practical programming point of view, I also found it interesting that in many strongly typed programming languages, there are clearly mixture of both. So even in, for example, Haskell, which is clearly trying to be a la Curry, they also have a way to explicitly express type for something. And on other hand, for example, C++ also now has a way of doing implicit typing. So it's a mixture of both. Now, when they are presenting what's more, what should be used, the usual selling point is like, it is easier not to express types when you program, or it is important to express types in order to ensure that you are doing the right thing. So my question is basically from the standpoint of mathematics, what what approach is kind of easier to tackle from a mathematical point of view, or is it irrelevant which typing you use?
Yeah, again, the mathematics goes more in abstraction, and what is usually investigated is whether a system can have both ways of defining. So most of the systems, for instance, this cube can be defined a la Church and a la Curry, both ways. But there are some typing systems that have only one of them, or mainly they have the Curry version, and if they have the Church version, it is easier to obtain the Curry version than the other way around. So, as you say, it is good to have both versions, and then use the version that is more appropriate for the given solution or for the given application.
Thank you. If there are some other questions, please.
Yeah, thank you, Professor. I had one question. Thank you for your talk. I think it's good to give this perspective on formal methods that basically are not so frequently used in engineering, unfortunately, but they could give us a lot of potential for thinking a little bit differently. I will try to tackle also this evening in a speech what is the practical way how we can assure, let's say, some certainty in some designs. But I think there will be times where we cannot do a practical evaluation, so we need some kind of formal checking. And I was participating in a, let's say, study program recently where we tried to understand the formal methods and their applicability to autonomous cars and autonomous driving. But the only example that we used in LTL model checking, encrypt key structures, etc., were electric cattle and traffic lights. So these were like very simple ones, having the several states, you know, that you could intuitively figure out when you do the checking, you even intuitively know whether it's correct or not. And I imagine if we have a much more complex system to formally check, then the intuition stops there. So you need to trust the methods and to trust the math behind it. So my question would be, what is your impression on the applicability of this in the context where we need to argument the safety and the certainty to somebody? So it's, you know,
I know exactly what what is your question about. So sometimes, you know, formal methods are very costly to use. So I attended a talk where they said they were, you know, in NASA, they were in 7 years, they found 2 bugs. So the whole NASA team working on 7 years on 2 bugs. So this is, maybe it's easier just to let those bugs out there, and less expensive. But nowadays, this problem of self-driving cars, this is a completely different problem. So you have this problems, so that bug can, you know, can be in every car, in every software. So I mean, now it is really very important for these things to develop formal verification. But then, as you said, how to trust formal verification? So where maybe this formal verifier will be also formally verifier. So till where do you go with formal verification? Yeah, this is really, but you know, this is like the statistician who does not like to, who is afraid of flying, and then because there are bombs in airplanes, and then he takes his bomb with himself on the airplane, because the probability to have 2 bombs is, you know, you multiply the probability. So in this sense, we have to stop somewhere with verifying, and each verifier will diminish the possibility of the error. I know that from the applicative part, this kind of question, this kind of answer is not an answer, but this is at the moment the only way out.
Yeah, I get it. It is good to speak about this. I think it's the great placeholder also, and I'm happy that we have this talk also within ZINC conference, because I think people are very generally speaking that, and ZINC has the broadest possible audience in technology, are not that well aware of what can be formally assessed, actually. And I think it's very beneficial that we have a chance to listen to this. Thank you very much.
Thank you.
Yeah, that could be a topic for some other panel.
I'm looking forward to your talk.
Are there any more questions? If not, there is a lunch break and we continue at 2. Thank you again. Bye.